Thanks everybody for attending our talk. I'm Matt Peters. I'm the Chief Product Officer at Expel. With me is Pete Silberman. He's our Chief Technology Officer. We're going to be talking a little bit about optimization and queuing theory as it applies to security operations. So in the talk, what we're going to talk about is a general idea of queues and queuing. So how does queuing theory work? What's the math behind this stuff? We're going to talk a little bit about a simulation framework that we've used to actually simulate our SOC operations here at Expel, and then actually make incremental changes and sort of show the application of certain optimizations we can make in security operations. So to start with, we have a sort of a canonical diagram of a queue. So jobs, represented by these little green boxes, move through the queue from left to right. When work shows up, it enters a waiting area, which is that little white box. And you can think about this like the line at a movie theater concession stand or a waiting room in your doctor's office. If you show up and there's nobody ahead of you, go right in and get processed. If there is someone already being processed, you wait in the little queue. In this model of the queue, there's only one class of service. Work's handled in the order it's received, and it's handled by the worker, which is represented by the little white circle. So there's a couple of parameters that are sufficient if we specify them in this queuing system to actually totally understand how it's going to behave. So the first one of those is how many servers there are, how many little circles. This is how many people are working the concession stand, how many workers you have in your SOC, something like this. The second parameter is the service rate, how fast those workers work. So if this is a rate, jobs per second, tickets issued per second, something like this. And the other parameter is arrival rate, how fast are jobs showing up. So again, a rate, jobs per second, customers per hour, something like this. And the last parameter, which we mentioned, was classes of service, like is there a high queue and a medium queue? Is there a priority of VIP line? Something like this. With those four parameters, we can actually totally understand the behavior of this system.
So since this is an observability conference, we're going to take a second here and talk about some of the various things we might monitor if we were running some kind of queuing system in production. First, we're going to want to track how many things are going in and out of our queue at a given point in time. Setting a simple threshold here that tells you when the number of jobs waiting to be serviced, so these are things that haven't gotten serviced, have exceeded acceptable limit, is a pretty good idea. If you're familiar with Kafka, for example, this can be thought of as a monitor on the consumer lag, which is just how many things for a given consumer group are outstanding, basically waiting to be processed. These types of monitors can indicate your arrival rate has greatly exceeded your service rate, and that you may need more servers, or that something has happened to your servers that you want to go check out. And then if you're successfully processing n events, there's a couple intervals or durations that we're going to want to grab that might be worth keeping an eye on. The first one is the time from when the job enters the queue and exits the queue. That's going to be the wait time, and that's T1 and T2, T1 minus T2. Then you have the time from when a job enters and exits the actual service. That's T3 and T4. That gives you the service time. You can use the first and last timestamp, T1 and T4, to give you the end-to-end latency. All of these things are good things to think about and surfacing and watching as you think about monitoring your queues.
So given those simple measurements, there's an amazing amount of stuff that we can figure out, and this is sort of the rest of the talk. But when we think about a queuing system, one of the things we want to think about is there's sort of three relationships between arrival rate and service rate that determine where we're going to be. So first, our arrival rate could always be less than our service rate, at which point, it's going to be awesome. You don't need this talk. You can get back an hour of your life. The other relationship that's sort of canonical is your arrival rate is much greater than your service rate always, and in that case you're going to have an endless line. It's going to build up until your service finally collapses. Those two regimes aren't particularly interesting from a queuing theory perspective. Where it gets really interesting is this middle part where our arrival rate is about equal to our service rate, but they both vary. Because what we can do then is we can do a lot of tricks. We can introduce various tuning parameters and things like this to actually control how our system performs. So what are the kinds of things that we'd actually tune for is the other thing that we want to think about. The first thing is overall throughput of our system. How fast can we get jobs through this? How many jobs per second could we process? How many customers per hour can we put through this thing? That sort of stuff. Turns out for the kind of work that Pete and I do, that's only really useful at a macro level for budgeting and hiring and headcount. What we're more interested in and what's more relevant to our day-to-day is the latency. How long does it take from something showing up in our system to something being done? Because for security, for instance, if it's ransomware or something like this, you need to deal with it really fast. And there are a lot of sort of customer satisfaction issues around things like support organizations and stuff like that, where latency is actually more important. And the last thing to think about and that we can measure and observe is utilization. How busy are the servers, depending on the structure of our environment? This is effectively, are your people overworked? Are they about to quit? So in the real world, we see queues all the time. And one of the things, I'm a bit of a nerd about this. So like when I go and I see a system like the one that we see here that with this TSA line, I start looking at the stuff that they've done. So the first thing that we notice is, like, whenever we show up at a system like this, is we notice this rope line and we're sort of going through this like maze to get to the front. That's called buffering. And what they're doing is they're allowing work to stack up if they end up with a burst. So if there's a lunch rush, or at the airport, everybody leaves at 8 a.m. to go on vacation, that work can stack up in an orderly way. The second thing you notice is when you get to the front of that, there's multiple different TSA agents. That's multiple servers, more capacity. What that means is that they can parallelize processing and throughput overall goes up. Third thing we notice is that there's different types of lines. Like there's a pre-check, and now there's a clear, and there's a normal, and then in some airports they have one for first class passengers. And what that does is, by dividing up those service classes, you can control more fine-grained the latency that each one of those service classes experiences. And the last thing, and this one's a little harder to spot, but I always think it's interesting, is they are filtering here. If you look to the left of the photo, you see people lined up and they can't go into the security line. They won't process everybody. You have to have a ticket. If you've ever groomed a backlog, if you've ever adjusted tuning parameters on a security device, you've engaged in this notion of filtering. Doing less work is actually one of the best things that we can do to make systems more efficient. So in every queuing system, we have all of these knobs. You know, the TSA is trying to optimize for number of passengers per unit time at the lowest cost. But we need to understand that while they're doing that optimization, there's a bunch of things that exist in tension with each other. If you add more buffering, what ends up happening is your latency will likely go up. If you add more capacity, your cost will go up. So you have to decide what the constellation of parameters is that you want to optimize and how you want to optimize them to deal with those trade-offs. One of the things that's interesting, there's a bunch of math that you can do to actually try to figure this out, but the math breaks down pretty quickly when dealing with a system that's at all complex. So if we wanted to answer a question like, what if the TSA needed to start checking people's shoes, but they cut the number of people in pre-check by 50%, what would happen to overall wait times? We could try some math, but that's actually not going to work. What we'll end up needing to do is we'll end up needing to simulate. So that's sort of the remainder of our talk.
As Matt alluded to, the best way to figure out these things is simulating them. And so having the computer actually pretend that the work is being done, performing a number of runs, sampling them, and from those samples, we get the observations that help us understand the impact of checking shoes but cutting the number of people in half that TSA sees. So for this presentation, we're using Python. It's got a number of packages that would allow you to do various types of queuing simulation. We've found and really like a package that is spelled CIW. It's pronounced Q. We didn't write this package. We've become pretty big fans of the flexibility and just basically how it's built as a framework. What we're showing in this slide is actually a really simple queuing system. It's got one server with constant arrival rates. What you can see in the code is that Q is going to help us simulate all of this. We define what Q calls a network, which is just a simulation. It includes jobs that arrive at some rate and get serviced at some rate. We can specify our arrival rates in arbitrarily complex ways, including based on historical data. And for our talk and upcoming slides and simulations we'll walk you through, we're actually going to use historical alert arrival rates, Expels observed across all our customers for the past year. So it'll be pretty accurate and pretty realistic. Once we've built our network, we can ask Q to simulate to create a run for some number of ticks. What Q is actually going to do here is use our arrival rate and service rate functions as random variables. It's going to select the first arrival rate from our distribution. In this case, our distribution is deterministic, which means it's just going to return 4 or 5 respectively. It will then move the simulation time to that point and create a sample event. When the event gets serviced, Q is going to select the service time from our service distribution. Again, it's constant here, and add that to the simulation time. In this way, it can build up a time-based picture of the path each work item takes. You're probably familiar, this type of simulation is called a Monte-Carlo simulation, as it's using a probabilistic distribution to just approximate real-world systems. For this talk, we've built a generalized dashboard that we're going to reference throughout our slides. And this shows us, for this example and all subsequent examples, the throughput of our system, which is a little less than a quarter of a job a minute, which makes sense because the service time here is 5 minutes per job. It also shows us our utilization, which is up right around 100%. And then two distributions shown below are latency, which isn't much of a distribution here because everything is taking the same amount of time, and the wait time. Finally, if we look down, we can see that the arrival rate is a constant tick of 4 because of the deterministic distribution, and our latency is growing as work stacks up on us.
So that example isn't super interesting. Everything's constant, and actually the system's blowing up because the arrival rate is slightly greater than the service time. So as a result, we're falling behind. But in this case, the real world doesn't really work like this. So the power of a system like Q and the power of things like Monte-Carlo simulations is our ability to simulate arrival rates and service times that are more of a probabilistic distribution. So in this case, instead of saying the job will always take exactly 4 minutes, what we're going to do is we're going to say the job will take about 4 minutes. And so in this case, what we modified is the arrival rate and service time distributions have become exponential variables with averages that are 5 and 4. We changed the averages a little bit too because it'll make the display a little bit more interesting. We're able to actually keep up with the work. Same exact rest of our parameters. One thing to note is that our ability to specify these things as exponentials allows it to map closer to the real world where, things tend to have a long tail and independent arrival rates tend to approximate sort of exponentials. So if we take a look at the results of running this, what we're going to see is a couple things. So first off, our throughput is about what we'd expect. It's about, we're servicing these things at 4 per minute, but they're arriving at 5 per minute. So that's really our gating factor. The total number that we're getting through is about 5 a minute. Our utilization is down, actually, which is quite nice, and that's because we're actually able to service them faster. So there is a little bit of time where a server might be idle waiting. When we look at the latency distribution and the wait time distribution, the other thing that we're doing in the dashboard is we're actually plotting this against the previous run. So if you look at the light green bars, that's the run that we had before where the system was blowing up. And basically the latency stretched all the way out to infinity because as more and more stuff stacked up, there was longer and longer waits. What we see for our current run in the dark green is that our latency is actually packed pretty closely up around 0 because things aren't having to wait that often. That's a sign of a system where we have low latency and we want to, over time, as we optimize our actual SOC, pack the latency and the wait time distributions up closer and closer to whatever our target is. The last thing we'll take a look at is the latency time series. You'll notice that there's a light green line that kind of proceeds on upward to infinity. And that was the previous run where we weren't servicing stuff as fast as it was arriving. So stuff was just stacking up. The wait times and the latency were just increasing over and over and over. The dark green line down at the bottom is our latency for this system where we're actually able to keep up. So you see it's a little bit of a jagged line because every now and then work stacks up because the arrivals might have a burst, but then we catch back up. This is beginning to simulate a pretty real world kind of system.
So roughly 10 slides into this and you're wondering, hey, I came to this talk and I wanted to hear about security operation. How does any of this apply to me? Fair question. When we think about abstract Q models, they apply most directly to any work-related function. A SOC where jobs are alerts and the servers are the SOC staff and the output is dispositioning alerts, writing reports, or an SRE team where the jobs are tickets or pages, the servers are the team members, and the output is close tickets, resolve pages, or improve features. In each of these cases, this kind of modeling can help us understand this really intricate dance between utilization, which is how your team is feeling, throughput, which is how much work you're getting done at a gross level, and latency, which is the SLO your team is trying to meet. And so now we're going to move to more specific examples with a SOC.
So for the rest of this talk, we're going to talk over the SOC that we built here at Expel, including the optimizations we've done and how that's impacted our work. As we've said before, we need to model a probabilistic distribution, so we're going to use historical data to do that. Starting with our primordial UR SOC, we take security alerts in from a big pile of devices at lots of different customers' sites. This is represented by the multiple streams of green pseudo work on the left. In order to properly simulate this, we'll need to have an arrival distribution that mirrors the things that we've seen from this historically. And so the way that we've done that is using a feature in the Q framework that makes this pretty easy. What we need to do is we need to understand what our arrival distribution looks like. So looking at the graph, one thing that we should note is that there's bursts in it, right? So that means that whatever distribution we build is going to be relatively wide. It's going to be somewhat spread out because some of the rates were relatively high and some of the rates were relatively low. The second thing that might be slightly less obvious is that there's a periodic nature to the signal. And actually what happens is there's two periodic signals. One, there's a weekly periodicity where every Thursday looks about like every other Thursday, and we see a rising and falling action where weekends there tends to be a lot less action than there is on, say, a Wednesday. The other thing that we note is that there's a 24-hour oscillation as well. So we note that 2 a.m. things are relatively quiet, and at 2 p.m. things are relatively noisy. And so there's both of those oscillations going on. What that means is that we're going to need to try to model that and figure out how do we deal with both of those things and simulate them. We've provided all of this data to you. It's available in this arrival time CSV. So if you want to take a look at it and try your own modeling, you can. So taking a look at how we built the historical distribution. So one thing that we did is we can take a look at the historical distribution, and because we understand the periodic structure of it, we can actually look at it and say, hey, every Tuesday at 10 a.m. looks about like every other Tuesday at 10 a.m. So what if we model every Tuesday as its own exponential? And so what we did was, if you look at the arrival rate over this 6-month window, the little red dots represent Tuesdays at 10 a.m. We took those out as a sample, and then we built a Tuesday at 10 a.m. Subsample, which became the basis for our exponential distribution in that day and hour. Our historical distribution then, when we go to do a sample, will pull the right day and hour exponential and pull something from it. There's a lot of different ways we could do this. We tested it out, and this one was the one that gave us sort of the best results that were the closest to what we kind of experienced. So taking a look at that and what that looks like in code, our historical distribution here, what we do is we inherit from the distribution object that's provided by Q. And the main thing we need to implement is a sample method. The sample method gets called whenever Q needs to ask a question. How long did something take, or how quickly did something arrive? And it'll pass in two parameters, the first one being the time that the simulation is currently at. So what we do is we say, okay, based on that time, let's figure out what hour and day we're in. Let's find our right distribution, and let's pull a sample out of that. So that's exactly how we've done that. It makes it super duper simple. The other thing that's cool about having this simulation time in this method is we can actually do something like we could simulate day shift and night shift if our service times were different, or we could simulate all sorts of different time-based effects that we wanted to. So that's how we built our historical distribution. So the second thing that we did was we had to go ahead and model our service distribution. This is to say we have to have a distribution that models a bimodal that represents how our SOC works. So the state machine for how our SOC functions is in the diagram at the top. Work enters from the side, and basically analysts do what we call triage. It takes them 4 minutes, and they look at an alert and they say, hey, what's going on? Is this a thing? And they'll say, this one isn't, and they'll close it out. So that alert gets dealt with in 4 minutes end to end. Some alerts aren't clear, though. We don't know. And so they're going to move it into an investigation stage, which takes longer, usually somewhere between sort of 20 to 45 minutes of fetching new information, figuring out what's going on, and then actually reporting that. So then what we've done is we've modeled that by, again, inheriting from a distribution object and creating this service distribution, which is parameterized by 4 things. The first one is the time to triage, which in our case is about 4 minutes. The probability that something turns into an investigation, right? And then the time to investigate and report. And when we do a sample, we basically say, if everything gets triaged, so everything's going to take somewhere around 4 minutes based on an exponential distribution. And then some things will take an additional amount of time if they turned out to be investigations. We're going to play with all of these knobs as we move forward. So putting that all together, the code ends up looking like this. And what we've done is we've parameterized it. So if you are following along in Docker and want to play around, all of the variables that we're talking about are in all caps, and we set them to start with time to triage, investigate, report, how many SOC workers we have, and how long we run the simulation for. We have our historical distribution specified, and then all the way down at the bottom, what we'll see is we'll see a run, which is just the standard queue run that we're familiar with, passing in these distributions and running them. So what happens if we run this? So in this case, what we're going to see is that we're putting through not that much stuff. We're about every 0.8 of a minute we're dealing with something, and we have a utilization of about 99%. Our one poor SOC worker is going to quit. The other thing to notice is our latency and our wait times are pretty uncorked. For the purposes of our SOC, we've actually got a service level objective, an SLO, that we want the latency to be below 30 minutes end to end. So we want the things to take less than 30 minutes from the time it shows up to the time that we actually do something about it. And we want the wait time, the amount of time before a human being puts eyes on it, to be less than 15 minutes. And those are represented with these red lines in the latency graphs. And you can see that our distributions are vastly outside of that window. So the job of us for the next few minutes is to try to figure out what knobs can we throw to make this true, right? To make it so that we meet our SLAs.
All right, so the first knob we're going to start looking at is adding capacity. If you've ever heard the saying, throw bodies at the problem, this is what we're doing. To throw bodies, we're going to indicate the new capacity by adding another server to diagram. And we're doing this in the code by just increasing the num server parameters we're passing to the model. Remember in our simulation, adding another server is us adding another person. And this might not actually be the first step in a real SOC, since adding capacity or throwing bodies at it actually means you're hiring. And that's both expensive and hard to do, especially in security. But it does have impacts that are both direct and indirect to your ability to service the jobs coming in. What's going to happen now is when work shows up in the queue, there will be two workers who could potentially grab it. The system will automatically choose one of them, start working it, and if a new job shows up while that server is busy, the second server will grab it. So let's see what that did to our dashboard. As we saw before, this has a direct impact, which is that the total throughput of the system is now doubled. We've increased it because we've added two workers. The other perhaps less obvious impact is latency is going to go down a bit since there will be less head-of-line blocking. What it looks like in the dashboard is that the latency distribution curve is shifting to the left. That dark green is our current run, so we've moved it to the left. It's tighter on that side. And you can see that the light green, which is the previous run before we had two people, spills out further to the right. One thing we still see is that we're still having head-of-line blocking issues, and we can see that in our wait time distribution. It's still spread out. But if we look at the latency time series, we see that we're much better off. We don't get uncorked like we did before. It's a slow, gradual slide to madness. But there's now, what else can we do?
So the second big bang for the buck that people get, and this is kind of an interesting one, is training, right? The way that we're going to model training is we know from experience at Expel that a junior analyst or somebody new working in the SOC will have a tendency to take a little bit longer on triage. They'll tend to make more investigations. They'll tend to be uncertain, and rather than closing things out immediately from triage, they'll tend to promote more things into investigation. And those investigations will take slightly longer. So the way that we're going to simulate triage here is we're actually going to reduce our time to investigate, our time to report, and our probability of investigation. So we're saying effectively we'll have fewer investigations and they're going to take less time. I want to call out, as we look at the data and the dashboard from the run, that this actually has a pretty marked impact. So let's take a look at that data. So note again, here our throughput has gone up some more. This is because the total time to service things is going down. The number of things we can get through will go up. That's just sort of a mathematical relationship. The other thing to note is actually it had a tremendous impact on our utilization. Our utilization is down about 10% now. And that's because we're spending less time, being busy doing these investigations. We reduced the time pretty significantly on that. It's had another good effect on our latency. If you look at the light green, and this is a little bit harder to see, but the light green spread is pretty far out to the right, and we're actually tightening up. It's getting closer and closer to being clustered around our SLO, which is exactly what we want. The reason for that is to go back to this notion of head-of-line blocking. If you're at something like a toll booth, and there's a semi-truck in front of you, what's going to happen is you're going to wait, even though you've got easy pass and you're going to just cruise through this toll booth, you're going to have to wait for the semi to go, and it's going to take a while for it to stop. They're going to have to pay $10 in quarters, and then it's going to be a slow acceleration. That's called head-of-line blocking. That's exactly what happens with an investigation in our theoretical SOC. If an investigation if an alert shows up that needs to be investigated, that takes one of our workers off the triage queue, and now they're investigating. If another one shows up and needs to be investigated at that point, everything else grinds to a halt. So by shortening the investigation time, we lower the probability that happens. Our latency and our wait times improve dramatically, and that's shown from both of these things. So that's a main thing. I can't stress enough that most of the security operations centers that I've worked in, they pay for people to get certifications and stuff like this, but a real investment in training people can have an outsized impact, and it's actually dollar for dollar probably one of the best things you could do for security operations optimization.
All right, so now we're going to look at tuning. As you may know, not all security alerts, JIRA tickets are created equal. Some are just a straight waste of time. The best thing we can do is to drop them on the floor and not do that work. In our simulated world, this will be us adjusting the arrival rate to be lower. The way we've done this in the simulation is passed in an adjustment factor to our historical distribution that basically cuts out 15% of the alerts we saw. In reality, the benefits are less across the board. What you'll find in a lot of systems like this is that 80% of the inbound work is due to 20% of the sources. We have some talkers that account for that 80% of alert volume, and you want to adjust those. So let's take a look. One thing to keep in mind here is that while the arrival rate is lower, the work still takes the same amount of time as it did before. If each alert took 4 minutes before you tune, they're still going to take 4 minutes after. You'll just have fewer alerts. This implies is that you should take a hard look at how you're spending your time, how long you're spending on each alert, and optimize whichever tune will save you the most time. If you have one type of alert that takes 1 hour and one that takes 5 minutes, but that one that takes 5 minutes shows up 20 times, you want to optimize that one first because it's actually costing you more time. If you're designing a system, you want to be able to do the analysis of what the top talker is. This requires some data and the ability to get metrics off of it. Most sims, if you're using a sim or logging platform, have to be able to slice and dice this data so you can kind of do this regularly and build process around it. As you tune more, you'll have more capacity. Your utilization will go down so you can tune some more and train some more, and it's a double win. So we've done all this. Is there anything else we can do to improve on the system?
So we talked a little bit earlier about this notion of service classes. So let's say, I end up in a VIP line. What I can do is if I organize it so that there's fewer people that get admitted to the VIP line and I service that first, then the latency or the wait time and the overall throughput of the VIP line can be very, very high. The reason I might do that is because in security operations, for instance, a ransomware incident needs to be dealt with quickly because it'll be spreading and encrypting disks as we go. So the longer it takes us to respond, the worse it's going to be. If somebody's wandering around with domain credentials and they're accessing servers and they've got like the keys to the kingdom, they could be doing all sorts of damage while we're waiting on doing some lower priority work. So what we do is we want to introduce some sort of service tiering where we say we have some number of high priority alerts. We classify certain classes of things as high, and those always get dealt with first. Some other ones that are dealt with as mediums, those get dealt with second, and then we have some low severity ones. And the way that we do that with Q is that this is a common enough pattern that it's built directly into the Q framework as being able to supply these classes. So what we do is we say we have 3 service classes in this case, and we're going ahead and setting an arrival rate and a service rate for each one of them specifically. What that'll do is that Q, as we run the simulation, will deal with the highs and then deal with the mediums and then deal with the lows. And if it's in the middle of dealing with a low and finishes up, it will go back and check the high priority queue first before it does anything else. So if a high shows up, it shouldn't have to wait as long. So let's see what that actually does for us. So in this case, there's a little bit of an adjustment on utilization, but quite frankly, that's kind of in the noise at this point. Our throughput is about the same, but that's not actually what we're trying to optimize for. We're not trying to improve throughput here. We're really trying to talk about latency. But you'll notice our latency improvements, we have a little bit of an improvement. The green line all the way on the left for latency has a slightly taller peak around below the SLO, and our wait time distribution is a little bit better, but not by much. What we really want to do is we want to see the impact of what happens to the high priority data, and we plotted that separately. So this is actually the latency of things that were tagged as high severity versus things that were tagged as low severity. And you notice that the latency clusters almost entirely around 0, that is to say, or around below the SLO, that is to say that things in the high priority queue aren't waiting at all. This is why sometimes it does pay to get that VIP access or something like this, because you just won't wait as long.
So now we're going to talk about tiering. We've got the service classes, tuning, and a bunch of other optimizations in place, and we're still looking to deal with a pretty serious issue, which is this head of line blocking. This is the phenomenon we've all experienced. If you've ever been in the grocery store and there's only one checkout line and the person in front of you has groceries to feed an army, they're paying with a third-party out-of-state check and using coupons, you've dealt with this. No matter how few items you have, you're blocked behind this person, you're going to have to wait. We've already improved our performance a bit by separating the inbound work into a set of service classes, and now we're going to separate the workers into a set of service tiers. If we can do this in a way that one group handles the work that is less frequent but more time-consuming, the investigations, it can free the main body of the SOC to handle the more common, fast-removing work, which is triage. This is like the express checkout at a grocery store. The way we can handle this in Q is to change our simulation into a network. We're simulating a network still, and we basically want to take a step and break each step onto its own server. So these are annotations 1, 2, and 3. What this will do is say triage is its own process. So these servers aren't contending with an investigation. What we then do is define a network, and that's the standard routing network, to connect these things based on the probability that a job moves from one of these nodes to another node. In our example, that's annotation 4, which basically defines the routing between our nodes as a transition matrix. The first row says the transition probabilities out of triage are 18% will move to investigation and the rest go to done. The next row in our matrix says everything from an investigation moves to done. The power of this is that all these what-if scenarios are available to us to play with, and we can move things around to see if they really impact or move the needle for us. The main thing to call out here is that we've added utilization of our two tiers. So we now have utilization for triage and utilization for investigations. Our triage folks are doing okay at about 73%, and our investigation folks are working at 4% utilization, so they're doing fine. Our SLOs and wait times are beginning to look really healthy. We have a few outliers, but we're really moving to within that 95 percentile of our SLO.
So the last optimization we're going to do, we've broken out service classes. So we have high priority stuff screaming through the system. We've broken out our investigation and our triage into separate steps. Is we're going to add some automation. And we did this last both because it's useful to build up the system first, but the second thing is it's actually useful to have good time on target to understand what to automate. If you end up automating something that you don't do a lot of, it's not going to end up benefiting you. But if you have a thing that you do a lot, automating that will actually save you a bunch. That sounds like sort of motherhood and apple pie, but at the end of the day, I oftentimes go in and see operations where they've automated sort of the 0.001% task. The way that we're going to simulate this in Q is we're actually going to change our service distribution for our investigation node. And we do that by creating this auto investigation distribution. Again, inheriting from the standard Q distribution. And what we've done is we parameterized one more thing, which is the probability that the work is automated. The way we're thinking about it, if you automate something, if you say like, okay, I get a piece of, I get an alert about malware and I'll automate the fetch of the malware, the detonation of the malware, and the classification of it based on a script, that work time effectively drops to 0. No one is contending with that because you have a robot doing it. So what we do in our sample method here, annotation 1, is we effectively say there's some probability that the work is going to be automated. And if that's the case, just return a service time of 0. What that should do is it should end up improving our investigation throughput and our overall latency for those things. And so what we see here is, if we look at the utilization of our investigation tier in the upper right, that dropped. We basically cut it in half because we've automated a significant chunk of that work, which is super awesome. The other thing that's instructive is our throughput did go up a little bit, not by a lot, but a little bit. And we'd expect that because our total time to process something that needed investigation is also going to go down. So units of work per time would go up. One thing it did not do, however, particularly, it had a little bit of an impact on latency. You see the green bar poking out above our light green bar right there by SLO. So we have a little bit of improvement in our handling of SLOs, but it's not that much. And the reason for that is because we actually automated something that we don't do a lot of. You'll recall only about 18% of our stuff needs investigations, and we only automated a percentage of that. So the overall impact of the system was pretty minimal. Exercise to the reader might be if you go in and you actually take this same service distribution and put it, attach it to our triage time, because now most of our time is being spent in triage. You can probably get our utilization significantly further down. Just to call out where we are and where we've come, we've added all of these optimizations to our system, and we now have server utilization that's around 73% for our triage tier, so our front tier 1 analysts, which is actually pretty good from an industry standard. Our investigations, we have utilization around 2.4%, so our senior analysts are free to do lots of different stuff. We've actually crowded up against our latency and wait time distribution SLOs, so we're doing pretty well there. We have a few outliers that we need to deal with, but we're for a 95th percentile SLO well in hand, so we've actually accomplished a tremendous amount. So overall, in conclusion, the main thing we want to leave with is, one, as you're optimizing a system, try to understand what you're optimizing for. Are you optimizing for latency and wait time? Are you optimizing for throughput? Are you optimizing for cost? What are the parameters? What are the things in that constellation? Second thing is try to change one variable at a time. That's sort of the process that we went through. If you change multiple things, the crosstalk effect might actually cancel each other out, and you think you didn't make an impact when actually you did. And then this sort of simulation, while it doesn't 100% reflect the real world, if you lead in with good assumptions and sort of understand your data and where it goes, it can actually help guide modifications in your actual real world process. Thanks so much for attending our talk. We really appreciate it.